Hey guys, I hope you're all doing good. Now that we have covered boundary flagging and some surface errors, we are going to be setting up a simple case. Now the way this is going to work out is I'm going to show you the geometry and I'm going to be setting it up step by step, and I'll also be explaining my thought process. So once I complete that, you will be creating this geometry from scratch using Studio and you will be setting up the case. At the end of this video, I'll also be teaching you how you can create primitive shapes using Converge Studio. Alright, so the problem that you are looking at is called as a backward step, and we are going to be simulating flow over a backward step. This is a very important problem in computational fluid dynamics. Oftentimes when people develop new turbulence models, they test their code on this particular problem because for this problem there is a lot of experimental data available. So in this particular case, I've already created the geometry and I've already exported a STL file. So now I'm going to launch Converge Studio and then I'm going to create a new project. So then what I'm going to do is I'm going to import my geometry. All I'm going to do is just drag and drop. So as you might know, Converge requires the geometry to be in meters. So one thing you can do is you can go to options, geometry bounding box, and here you can see that clearly this is actually a geometry that was made in millimeters and was read in Converge. So there's no way that this is actually 272 meters long. So I'm going to first scale this. As I said before, anything that has to do with the geometry, the tool is going to be on the left hand side. So in this case we are trying to transform, basically we're trying to scale, right? So I click on transform, scale, and I'm going to scale the entire surface and I'm going to convert meters to millimeters. So there is a factor of 0.001. Click apply and then you will see that the geometry is gone. That's because it has been scaled down. So don't worry, if you just click on one of those standard views, it's going to appear back. And this time you can see that the bounding box has been updated. I no longer require it, so I'm going to hide it. All right, so this is my geometry. So what is the first thing we need to do? We need to make sure that the geometry looks okay. So first we run the diagnosis, obviously no errors. And next I check the normals. So here you can see that the surface normals are all pointing outside. So this is bad. We want the normals to be actually pointing inside because we're trying to simulate the flow inside the geometry. So I'm going to quickly transform the normals. All right, that's perfect. So the next thing that we need to take care of is we need to group these triangles into boundaries, right? And that is where boundary flagging comes. So I go to boundary, flag, and I'm going to be creating multiple boundaries. And you can see that here the feature edges are quite nice. So if I just use the angle method, that should be fine. For example, I can say that this is my inlet boundary. It's already boundary number 1, so I don't need to do that again. And let's just add this side boundary to boundary number 2, this side to boundary number 3, and for the top and wall I'm just going to add them to the same boundary. Okay, so I'm just going to add it here, and finally these two triangles. So I flagged all of my boundaries. The way I know that I flagged all of my triangles is by making sure that in boundary ID 0 there is 0 triangles. So this is something that you always need to check. Make sure that your default boundary ID does not contain any triangles. So here the sum stands for the number of triangles in that boundary. So you need to make sure that there are no triangles. So in this case we have one additional boundary, we can just delete it. So it's always good to give meaningful names to your boundaries. So this is going to be called as inlet. Okay, because the flow is going to come through this inlet face. And similarly this one is going to be called as outlet. So the way I renamed the boundary is I hover on top of so I click on the boundary name and then right click, and then I will be able to type a name for it. Okay, so this yellow boundary I'm just going to call it as front, and this one I'm just going to call it as back. And finally your top and wall, I'm just going to call it as top and wall boundaries. All right, so you can split the top and wall to separate boundaries, it really doesn't matter. So the type of simulation that we are going to be doing here is a 2-dimensional simulation. All right, so why are we doing 2-dimensional? Well, in the experimental data, the dimension along z-axis is so large that you can actually think of this as a 2D problem. So there is no variation along that axis. And for a 2D problem, obviously you can use more number of cells. So now that I've set up my geometry, I can directly go to the case setup. One nice thing about Converge is that you don't have to create the mesh manually during the pre-processing step. The mesh generation process is 100% automatic. So let me start the case setup. So in this particular case, I'm just going to do a general flow simulation. And for materials, I'm just going to start with a predefined mixture. I'm just going to take air and just click apply. It's going to load some default constants for solvers, so that's okay. So you can see that whenever you have finished setting up an item, there is a green mark that appears. So in this case, for global transport properties, it just wants you to take a look at what the global transport properties are. You don't have to change it, so just click OK. And then the next thing we are going to do is set up simulation parameters. So for run parameters, there's nothing that you change here. There is something called a simulation mode, which is full hydrodynamic or no hydrodynamic solver. So no hydrodynamic solver is used for testing purposes. For example, if your geometry has a lot of complex motion, you want to make sure that the mesh generation process is taking place correctly. So you don't solve any CFD or conversion equations. You just create the mesh at each and every time step. You make sure that the mesh looks good, and then after that has been taken care of, you can run the simulation in hydrodynamic mode. So in our case, our geometry is quite simple, so I'm directly going to run it in full hydrodynamic mode. With respect to solver, this is something that a lot of people think about. So in this type of a problem, the flow is continuous, right? So the flow comes through the inlet and the flow goes through the outlet. Even in reality, right, initially the flow field is going to be quite disturbed, but then after some time it's going to reach a steady state, or at least a pseudo steady state. So in this case, it makes a lot of sense to actually run this case using a steady state solver. And Converge provides two steady state solvers, pressure based and density based. In this particular case, we are going to use the pressure based steady solver. And don't worry if you don't understand what these solvers mean. We'll have separate lectures where I talk about what a particular solver does and how it actually computes the flow field information. All right, so in this particular case, we are going to do compressible flow simulation. And when you click on OK, again, it's going to ask you a question like, do you want to load some default values? And we just click on yes. The next thing we do is simulation time parameters. So here we are going to start the simulation at 0 cycles. Now remember that this is actually a steady state simulation. So cycle here means each iteration. Okay, so we are going to be running it for about 15,000 iterations, and say that the initial time step is 1e minus 6, and let us say that the minimum time step is also 1e minus 6, and the maximum time step is 1 second. So then you set up your maximum CFL numbers. So you can see that for convection, diffusion, and for Mach, there are different CFL numbers. So if you don't understand what CFL is, we'll be talking about that. But in general, you need to understand that these determine the stability of your simulation. And the smaller the value, the slower the simulation is. For example, if you're running a steady state simulation, you can increase it. But if you increase it too much, your solutions can blow up or your solution might not converge very well. Okay, there are a lot of parameters that determine what the outcome is. So in order to keep it simple, I'm just going to use the default values. All right. So then we go to solver parameters. Again, for solver parameters, we don't change anything. One thing you need to know is Converge can be operated both in finite volume and finite difference method, but for all the cases that we will be taking a look at, we'll be using finite volume schemes. So I just click OK, and we can now move on to boundary conditions. But before I move on to the boundary condition, I typically like to set up the regions. So just like we grouped triangles into boundaries, you can group boundaries into volumetric regions. Okay, so the reason why you need the volumetric region is to set up something called as an initial condition. Remember, we are solving a bunch of PDEs which require both boundary conditions and initial conditions. Initial conditions are given in the volume, boundary conditions are given in the boundaries. So I'm going to add a new region, and I'm going to say that it's completely filled with air at 300 Kelvin and 1 atmosphere. So that should be enough. For turbulence model, we're going to use RNG K epsilon. Though for these type of simulations, it's typically recommended that we use K omega SST. But for demonstration purposes, I'm going to go with RNG K epsilon. So the next thing that we are going to do is set up the base grid. Now the base grid, in this particular case, you can click on this guy, target cell count, estimator. Again, this is just an estimation. So for example, if I need 10,000 cells, I need 2 mm base grid. This is just an estimation. For simple shapes like this, the estimation is actually quite good. So in this case, what we are going to do is I'm going to go with 2 mm base grid. All right. In addition to that, I'm going to click on grid control and I'm going to add fixed embedding. So whenever you click on a parent object, you basically get a list of additional options that you can activate. So in this particular case, I'm going to be using fixed embedding. So fixed embedding helps us refine particular areas in the domain. So I'm going to click on fixed embedding, and what I'm going to do is add a new embedding, and I'm going to be adding something called as a boundary embedding. You will understand what this does once you take a look at the result. So the boundary that I'm going to be selecting is called as the top and wall boundaries. All right. Now I'm going to pick a scale of 2, or sorry, let me actually start with the scale of 1, and I'm going to make my embedding permanent. Now what does the scale mean? Well, you see that the base grid is 2 mm, right? So a scale of 1 means a cell size of 1 mm, and so what I'm saying here is near the top and wall boundaries, the cell size is going to be 1 mm. All right, so let's click on that. And for post-processing, there's nothing special here, and for output variables, nothing special. So the last thing that we need to set up is our boundary. So here what we need to do is for each and every boundary, we have to select the boundary type. So my inlet is going to be an inflow boundary, and what I'm going to do is I'm going to say that it's a pressure inlet, and I'm specifying total pressure of say 110325. All right, and I'm going to say that through the inlet air is going to flow, and that's basically it for the inlet, and the inlet belongs to region 0. All right, so make sure that all the boundaries are assigned to a particular region. So your front and back, that is the direction in which there is no variation. So that is the direction that you want to ignore to make this a 2D simulation. So I'm going to set this up as a 2D boundary. No additional information is required. Similarly, the back boundary should also be 2D. Top and wall boundaries, these are walls. So when we use a wall boundary, automatically what we do is for the velocity and temperature, we apply a law of the wall. We'll be talking about boundary conditions for turbulent flows in a later lecture. So for now, just use the default value. And at the outlet, what I'm going to do is make it into an outflow boundary, and I'm going to specify a static pressure of 1 atmosphere. So there is a delta P of roughly 10,000 pascals. Okay, and that is what is going to drive the flow. And in case there is backflow, we are going to say that the flow that's coming back into the domain is just going to be air at 300 Kelvin. All right, so looks like there is an error. So what you can do is right click and click on validate to see what the error is. Here it says that regions has not been assigned, so I can just click on this and just select the right region. Make sure that you double click. All right, so now I'm seeing green tick marks everywhere, so that means no issues are found. So I'm ready to export all of my simulation files as input files. So remember that Converge uses input files to represent the entire simulation. So let's create a new folder. Inside D:(Converge runs, and I'm going to call this backward step flow. And since we are testing out, I'll just call it as test case. Export everything. All right, so now we can open up Cygwin. So use the control plus scroll wheel combination to make the font size bigger if the default font size is too small. So let's go to D:, and Converge runs backward step flow and test case. So what I can do is I can just type in Converge, and the executable that I want is the msmpi min64.exe. So one thing that you can do is if you don't want to see all of the other options, right? Then what you can do is you can go ahead and put those executables in a different path, delete them from the default path and save it somewhere else. So that way when you type converge, only the MS MPI executable shows up. So I'm going to run this in parallel using MPI, and let's use 4 processors. And before I do this, there's a small thing that I want to do. Well, you know what, I'll first demonstrate what I want to do. So when I execute this, you can see that a lot of information is getting printed out. So I'm going to open up the input file. Again, you can actually use like Notepad or WordPad++ to open the input file. I'm using VI because I'm familiar with that. And there is a variable called screen print level. So that tells us how much information we are printing to the screen. So I'm just going to set that to 0. And now if I run the command again, so this time you can see that less information is getting printed out. And so here you can see that the cycle number is getting printed, the current time step and the time step limiter is getting printed. So what does this mean? It means that DT CFL is your time step limiter. In other words, the maximum CFL number that we have provided is limiting our time step. So the way you can increase the time step is by actually increasing the maximum CFL number. Converge uses a dynamic time step. It is taking a look at different flow physics and it's trying to determine what is the best time step to achieve a stable solution. All right, so currently this is a really small time step, but by increasing the CFL number we can just make it bigger. But for demonstration purposes this is totally fine. So we are just going to wait a little bit longer for the simulation to complete. Okay, so the simulation is complete. In total it took 98 seconds to solve the problem. So let's actually go to the output folder. In the output folder you have something called as post files. So this is the file in which 3D information is stored. And if I go one level up, I have a bunch of output files. So these output files contain averaged quantities. So let's do a couple of things here. So go to Studio and then click on the line plotting tool and then navigate to the folder where you have run Converge. So in my case it's d::converge runs backward step flow test case. Okay, so when you do that, you will immediately be able to see all the output files. So one thing you can do is you can just type in a filter and it's automatically going to pick the right file. All right, so here you can see that there's a file called mass average flow.out, and let's actually take a look at the mass flow rate through boundary ID 1. So what is boundary ID 1? If I go here to Converge Studio, every boundary has an ID, right? So boundary ID 1 is for the inlet boundary, and similarly boundary ID 5 is for the outlet boundary. So if I go back to line plotting, mass flow rate boundary ID 1 means that that's the mass flow rate through the inlet boundary, and you can see that through the inlet boundary, the mass reaches a steady state value. So similarly, if we go and check the outlet, which is basically column number 10, which says mass flow rate boundary ID 5. Again, boundary ID 5 is your outlet boundary. Here you can see that the mass flow rate has again reached a steady state. Now it is very important that you actually look at your physical results to make sure that your simulation has reached a steady state. All right. So similarly, the other interesting thing that we want to take a look at is your cell count. So here you can see that there are totally 4 ranks. So each rank refers to a particular processor. So you can see that each of the processor is having about 500 cells and the total cell count is about 2000 cells. So now what we are going to do is we are going to look at some 3D data. So I click on this post processing tab and the case name is going to be test. Again, you can give any name there. So and if I navigate to my run folder again, this time make sure that you are inside output, and I'm going to convert all of my files, right? So I have about 16 files here, and I'm going to convert all the cell variables. So here these are the variables that I will have access to in the post processing program, and I just click on convert. But before I do that, make sure that you select the file type correctly. So in this particular course we are using Nsight and ParaView, so you can use Nsight if you want to post process the result using Nsight. All right, on the other hand, if you have to use ParaView, you can just use the ParaView VTK inline binary format. Okay, So for this particular case, we are going to be using ParaView. Why is that? Well, the version of Insight that we have is free, and it imposes a maximum cell count limit. So when your cell count reaches beyond a particular value, you are no longer able to use the free version of Insight. On the other hand, ParaView is open source and it's free. So I'm selecting all the variables and I'm hitting convert. So this is going to convert all of my post files. So if I open Sigwin and go to the output folder, you can see that all of my files are available. So the next thing I need to do is launch ParaView. So let's open d:\softwares ParaView bin, and then I'm going to launch ParaView. So once ParaView is open, go to File, Open, and I'm going to navigate to my run folder one more time. d:\converge runs, backward step flow, test case, output. And the file that we are going to be using is called as test.vtm. Okay, the type is a group file. And when you do that, you don't see anything. The thing you need to do is you need to click on apply. So when you click on apply, you immediately see the geometry. So now when I rotate this, you can see that this looks a bit weird. Now the reason why this happens is, our geometry is a STL file, so that contains triangulated information, and our cells are going to be Cartesian. And initially when you load the case, it's going to look a bit weird. So what we need to do is create a cut plane and then visualize the computational cells. So to do that, so just select your case and then click on slice. So here you can see the plane that's going to slice the geometry, and I'm just going to select a plane that has a normal in the Z direction. All right, something like that, and then I'm just going to click apply. So when you do that, you can see that a slice has been created. Uncheck show plane option, and then you can put the geometry again in the straight view. So this is your slice. So one thing you'll notice is that the background color is set to white. That's not the default color. So what you can do is you can go to settings and color palette, and then select background, and you can pick any color that you want. So maybe I'm just going to use a black color here, maybe with a dark gray background. All right, something like this. So now you can see that your coordinate system is much more visible. So the next thing that we're going to do is we are going to take a look at the mesh. And to do that, make sure that you have selected your slice and then click on surface with edges. And there you go, your mesh is visible. All right, so to pan in ParaView, you just need to use your scroll button. All right, and here you can see that my mesh has been created, and this is the embedding that we did. All right, cool. All right, so now what we're going to do is we are just going to color this particular cut plane with velocity to see how the velocity profile looks like. So to do this, all you have to do is just select your slice, and then from the top just click on velocity. So this is my initial velocity field, and just go to the final one. It looks all red because your scale is messed up. So just switch to a different variable and then come back to velocity, and here you can see how the velocity looks like. So the peak velocity is roughly 16 meters per second, and here you can see that there is a region where the flow separates, and because of that the velocity is low. So qualitatively the results look reasonable. So then if I go to the first frame, and then if I click on the next frame, you can see how the solution progresses. Right, so you can see that the solution reached steady state quite soon. So we have been running the simulation for quite a bit, which was not required. Okay, so that's how you create a simple cut plane, and then how you visualize the result. So we can also take a look at your pressure and see how the pressure actually changes. Okay, so what you are basically looking at is static pressure, so not the total pressure. Okay, so the reason why your static pressure is increasing is because of the increase in area. So the next thing that I'm going to do is create a vector plot by clicking on this glyph icon and selecting velocity, and then let's just click apply. So you can see that the glyphs are quite big, so I'm going to use the scale factor to make it look a bit small. All right, and what I'm going to do is I'm just going to remove the mesh so that I can see the vectors quite easily. And what else can I do? I can also change the color for my vector so that it looks neat. So let's select our glyph, click on edit. Click on VTK block color, solid color, and then click on edit. And then let's give some nice dark color so that the vectors are visible. There we go. So now if I zoom in, you can see the vectors. The vectors look a bit shabby, but that's okay. You can play with the sliders a little bit more so that you get a pretty picture. And you can also reduce the number of samples to get a cleaner plot. All right, so again here you can see the recirculation zone. So whenever recirculation zone exists in your domain, your pressure is going to be higher, and you can see that happens. So you can see that happens here. So visually the flow looks correct, but in order to make sure that the results are actually correct, you would have to ideally compare it with the experimental data. So what you guys are going to be doing is you're going to be setting up the same problem, but the only difference is you're going to be creating the geometry in Studio, and I'm going to teach you how to do that. So create a new file, and the concept that we are going to follow is quite simple. We are going to first create vertices, and with vertices we are going to form triangles, and then once we form those triangles we are going to flag boundaries and then continue the same steps that I discussed in this video. So since we are going to create something, click on this create option, and we're going to start with creating a vertex. Alright, so the first point I'm going to just place it in the origin. Okay, so you don't see that because the origin is there. The second point, what I'm going to do is I'm just going to place it somewhere above the origin. So let me just call that as 0.1. So now you see that point. So the third point, what I'm going to do is I'm just going to place it a bit far. Again, when I'm drawing this, I'm not actually drawing the exact geometry. So you guys will be working on the exact geometry. I've also given you the drawing. So take a look at the drawing and create it. So for now, I'm just going to create another point somewhere here. So it's going to have the same y coordinate. The x coordinate, I'm just going to call it as 1.0. So I have another point here. So I'm going to create one more point somewhere there. All right, and then what I'm going to do is I'm going to basically create a point that is slightly in the negative y. So I have that. I have that. I have that, and then finally I have my 0, 0 plot. So you can see that I've created the 7 vertices that I need to form the front face of this particular problem. So once I've created my vertex, I can create triangles from 3 vertices. So I select my triangles. So that's triangle number 1, triangle number 2, triangle number 3, 4, and finally triangle number 5. Alright, so you can see that I've created this triangle. So the next thing I can do is I can either just copy this entire boundary and then paste it at a particular offset, or I can also select this open edge and then I can just extrude it, just like you would do it in a CAD package. So both the methods are correct, so I'm going to teach you both the methods. So the first thing is copy. I can just copy this triangle, and for the offset, what I'm going to do is I'm just going to be offsetting it in the negative z direction. So let us say minus 0.3. All right, so something like that. You can see that I've not selected all the triangles, or yeah. Okay, so what I'm going to do is maybe offset it to 0.2, and then for triangle I'm just going to select by boundary, select all the triangles. There you go. So now what you can do is, now that we have created a copy, we can go to create triangle, we can loft edges, and we can select the first set of open edge, the second set of open edge, and that's it. We end up with our geometry. So I'm going to Control Z and delete the copy. The other option is using sweep edges. So what you can do is you can select the edges that you want to sweep. So in this case, I'm selecting edges by open edge, and I'm going to sweep this in the negative Z direction, and the sweep amount is going to be 0.3. So this is very similar to extrusion. I think that was a lot. So maybe just do 0.2, select those edges again. All right, so we get something like this, and then finally go to repair, patch, select this open edge, hit enter, and that's it. So you can see that there are two options. You can also do copy, and you can create those triangles manually. So what I would do is go to create, copy, triangle, and make sure that I've selected things by boundary. And then what you can do is create triangle from 3 vertices, and you can do the process manually, but there's no reason why you should do this. The loft and sweep edges are much more easier to use. All right, so make sure that you complete this case. So let me just finish this guy. So make sure that you set up this problem from scratch based upon the drawing that I've given you, and then post-process the results, and then post your solutions. Okay, all right, I'll see you guys in the next video. Bye.